Okay, our next speaker is Adam Polek from Facebook Research, and he will present the work of translation of music genres and voices.
Okay, so hi, my name is Adam. I'm a research engineer at Facebook AI Research here at Tel Aviv, and I'll present my team's work on translation of music genres and voices. Before I begin, I would like to talk shortly about Facebook AI Research. The goal of Facebook AI Research is to perform open and accessible research, which is open and accessible for everyone. We follow 5 core values. Our first value is openness. We publish all of our work, and it is accessible for everyone. Additionally, the work that I will present today about music was open source, so you can download the code, train the model for yourself, and we even released the model so you can play with it and experiment with. Our second core value is freedom. Basically, it's fair, we can do whatever we want. We can research any subject that we wish, as long as we advance AI research. Additionally, we collaborate both internally with other organizations at Facebook and externally with other research institutes. Of course, the research must be in the cutting edge of technology. And finally, our research is done at scale. So at scale, it can be both in software scale, data scale, and of course, large compute scale. The first work that I would like to present is in the music domain. The work is a universal music translation network, done jointly with Noah Moore, Lior Wolf, Yaniv Teigman, and of course myself. The goal of our work is to create an automatic way to compose cover versions for existing musical recordings. So if, for example, we have a piano music, and we'd like to translate it into a trumpet music. A simple approach will be to first transcribe the piano music into notes and then synthesize trumpet music. So we can do that approach, but it is quite difficult because it is really hard for humans to transcribe music, and it is especially hard when there are multiple instruments. Additionally, existing algorithms can transcribe music to notes, but they do so with a large amount of error. Therefore, the approach that we suggest is end-to-end. We apply our method directly on the raw audio of the piano, and we generate raw audio of trumpet music. Another trait that we are interested at is universality. We want our method to be able to work on instruments that are outside our training dataset. For example, we can train our method on piano music, saxophone music, trumpet music, banjo music, and guitar music. But during test time, we would like to apply our method on flute music, which was not seen during training, of course. The output of our algorithm will be one of the domains that we trained on during training, and during test time, the input will be from unseen domain, but the output will be in one of the domains that we trained on. We call this trait domain generalization. So basically what we want to do is to translate between musical domains. The musical domains that I presented so far are quite simple, since they are composed of a single instrument. But musical domains can be much more complex. They can be composed of multiple instruments, for example, an orchestra, which is built from numerous instruments, or an even string quartet with only 4 instruments. And of course, when we talk about musical domain, there is also the issue of style, because Mozart didn't write musical pieces in the same style of Beethoven. So musical domains can be quite complex. But if you are actually talking about translation, why not use existing methods for language translation? Today we have great algorithms that can perform translation between languages and receive state-of-the-art results. And if you think about it, a sentence is a sequence of words, and music is also a sequence. Let's go over a generic algorithm for neural machine translation. So we have an encoder, which operates on the input sequence, and extract the context. The context is then being used to generate the output sequence. So if our input is a sentence in English, we encode it into a context, and then we generate the output sequence in French, for example. What this means is that in order to train our system, we need a dataset which is composed of parallel languages, that we have samples of pairs. We need the same sentence in English and in French. And in music, this is hard to collect, because Mozart didn't write the same pieces that Beethoven did, or an orchestra doesn't play the same pieces that a big band plays. Therefore, we rely on unsupervised training to achieve our goal. Basically, we expect our model to learn how to translate between the domains without using parallel examples. Our underlying architecture is based on an architecture called Wavenet AutoEncoders, which was first introduced by Engine et al. At ICML 2017. They used it, the Wavenet AutoEncoder architecture, to build a neural synthesizer, a synthesizer based on neural networks, and which is able to generate music. The Wavenet AutoEncoder receives as input raw audio. Raw audio is basically a very long sequence of numbers between -1 and 1, and the reason for it being very long is that a single second in audio is represented by 16,000 samples. So if, for example, we have 5 seconds of audio, we will already have 80,000 samples. So our encoder, which is a Wavenet encoder, receives the raw audio. It then applies a sequence of convolutional neural networks in order to extract a latent representation. The latent representation is basically a sequence of vectors, which is then being used to condition a Wavenet decoder. The Wavenet decoder uses the conditioning signal and the samples that it generated so far to generate the next samples in line. This generation is autoregressive because we generate one sample at a time. The actual architecture that we use slightly differs from the original Wavenet autoencoder because we use a single encoder, as in the original architecture, but multiple decoders. And the reason for that is that we have several domains. We have drum domain, saxophone music domain, trumpet domain, and so on. And for each, we train a different decoder. So we have a common encoder for all the domains. It is shared between all the domains, and we have multiple decoders. The problem with the architecture that I just presented is that the easiest thing the encoder can do is just segment the latent space. And by segmenting the latent space, it basically memorizes the input. It might take the input, compress it a little bit, but the output will be just the procedure of opening the compression. So what will happen is that the piano music will be in one segment, and the guitar music will be in another. And in such a situation, we cannot perform translation. Basically, we would like to combat this parrot effect. We want the network to do more than just encode and decode the input like a simple decoder. We would like it to understand the underlying musical principles. And the reason that we want that, or this big sentence, what it means is that we would like the algorithm to encode the music in such a way that other decoders will be able to decode it into new domains. So it basically needs to understand music very well in order to regenerate it in a different domain. To achieve this, we use two different techniques. The first technique is adversarial training. In adversarial training, we introduce a third network called domain confusion network. The domain confusion network receives as input the latent vectors that the encoder outputs. It then tries to classify what was the input domain that the encoder received. By doing so, it differentiates between the different musical domains. And basically, if we will return to the visualization of the latent space, it will try to segment the space. On the other end, the encoder tries to fool the confusion network. And it does so by being adversarial to the network. So basically, the encoder will try to generalize the representation, and by doing so, compress all the segments together, while while the domain confusion network will try to separate the vectors. Our second technique is based on distorting the input. So in a normal training scenario, what will happen is that a drum signal, Sj, will be encoded by the encoder E, the common encoder, and will be decoded by the decoder Dj, the matching decoder. During distortion of the input, we basically apply some sort of augmentation. The augmentation that we chose is done as follows. We randomly segment the input signal into segments. Then, in each segment, we slightly change the pitch to be higher or lower. And by doing so, we slightly make the music off tune. Additionally, we require the network to reconstruct the input, but the input has to be undistorted. And by doing so, memorization is no longer an option, since if the network will memorize the input, it will output the distorted version, and we explicitly require it to output a clean input. So this is our entire training scheme. We use two different techniques to avoid memorization. We have input augmentation, and additionally, we have a domain confusion network. And during training, we input a signal of a drum, for example, and we reconstruct it using a drum decoder. So basically, each input domain is reconstructed by its matching decoder. During inference time, we can take a domain that we saw during training, for example, the drums, encode it using the common encoder, and decode it using the matching decoder. We can also decode it using any other decoder of the instruments that we saw during training. Let's listen to some examples. Now we can listen to a much more complex example, because the domains, both in the input and the output, are much more complex and are composed of multiple instruments. We can also continue with domains that we didn't see during training. For example, a human whistle. Now I would like to continue to a different domain, the domain of human speech. And I would like to present our work, TTS-Skin Speaker Conversion via ASR, done jointly with Lior Wolf and Yaniv Teigman. Our goal in this work is to be able to customize existing text-to-speech interfaces with multiple new voices. And we are motivated by the fact that in the recent years there is an ongoing revolution in audio interfaces. So we can encounter audio interfaces in our cell phones, in our laptops, and even in our homes in the form of personal assistants. And we can probably say that text-to-speech is the best example of a deep generative model that is being used in production today. And the reason for that is that today we have high-quality text-to-speech interfaces. And this is thanks to recent research and models such as Wavenet and WaveRNN, which are able to output audio which sounds almost human. The question that we ask ourselves is, how do we scale to obtain personal text-to-speech, meaning a text-to-speech with a unique voice? So, in order to train a text-to-speech system, you will need to hire a professional voice actor, take him to a studio and record tens or even hundreds of hours of audio. And basically what we want to do is to be able to learn new voices using a small amount of data, and to do so in large scale. And the main reason to do that is that in the near future, everyone is going to have a personal assistant. And we would also like to differentiate between them by making each and every one of them have a unique and special voice. Our approach is WAV to WAV. It operates directly on the raw audio and outputs raw audio. For example, the input can be a sentence being spoken by a speaker, and the output will be the same sentence being spoken by a different speaker. Since we are operating directly on the waveform, and we don't rely on text, we can easily apply our method on existing text-to-speech interfaces. So we will take this text, we will use a TTS robot to generate some generic audio in some generic voice. And then we can use a skin to generate the audio in a voice of our choice. Our approach receives as input raw audio, as we said. We then encode the audio using a convolutional neural network. The convolutional neural network that we are using is pre-trained for the task of automatic speech recognition. Put simply, automatic speech recognition, or ASR, is a task of taking speech and outputting text. So what basically we do in ASR, we take the speech, and regardless of the identity of the speaker, we output its content. The architecture that we rely on is called WAV to letter, and it was developed by researchers at FAIR. Since the features that the network outputs contain only the content and not the speaker identity, they are very suitable to our task. So we take an intermediate the output of intermediate layer of the network as our features, which we call speech features. Then, we append to those features a vector representing the identity of the speaker we would like to hear. So this is the speaker that we will hear in our output. Then the concatenation is used to condition the generation in a Wavenet decoder. So the Wavenet decoder is the same decoder that I presented earlier. It receives as input the conditioning signal and outputs in an autoregressive manner the same sentence in a different voice. During training, we train our system to reconstruct the input. So if, for example, we take a sentence spoken by speaker A, we take the sentence, we extract speech feature from it. We concatenate the vector of speaker A, and then we generate the audio of speaker A. This is during training. During test time, we simply take the input of, let's say, speaker C, and then extract speech features, append the vector of speaker A, and we get the same voice of speaker A saying what speaker C said. Initially, we train our model on a large corpus of speakers. Specifically, we use 250 speakers with about 100 hours. So it's about 24 minutes of audio per speaker. Then we learn new speakers by simply fine-tuning the model using the data of those speakers. For example, we can use only 5 minutes of audio of a random speaker, and we can learn his voice. Let's listen to an example. So the first sample will be the sentence that I'm interested to convert. And here is the speaker of whom I have 5 minutes of audio. And here is the conversion. This was done using 5 minutes of audio. Let's move on to some applications of our TTS skins. First of all, we can now communicate with our friends in a fun way.
Hey, let's start the movie at 5.
I found windows today, you and your popcorn. I found windows today, you and your popcorn. I found windows today, you and your popcorn. I found windows today, you and your popcorn.
Sasha, can you give me a latte before the movie starts? Hey Sasha, can you give me a latte before the movie starts?
And if you're familiar with apps such as Lasso or TikTok, where you create a nice video of yourself for 5 minutes, then you can also customize it using audio filters.
Hey guys, doing a review of distortion. Espresso, it's got my cup, super excited. Hope you had it.
Raspberry, little chocolate, pretty sweet on the notes.
Let's head over to the next one, check it out.
I just got out of the coffee maker on the lawn. Here I have is this latte. Let's try how it is. Oh my god, this is so good!
And we can also listen to the developers of the apps that I just presented talking about their work.
Hey guys, check out this app cover that I built.
Whoa, cool. I think I see a bug in it. I'll work on it.
I know this new demo and everything, yeah.
Is that the same demo that's not the Yeah, it's called Wavenet. You guys like it?
So in my lecture, I talked about two methods in two different domains, music and speech. The first work was about creating an automatic way to generate cover versions, where we used adversarial training to do so. The second work presented a method to augment existing text-to-speech system using our approach called TTS skins. Thank you.
Thank you, Adam, for exciting talk. We have time for questions.
Yes, it depends on which data set. So basically, because we are dealing with generation, we always, in both articles, we used a mean opinion score, which is basically mechanical Turks listening to the examples and rating them between 1 to 5. In the case of TTS skins or voice conversions, there is a challenge called voice conversion, where basically you have speakers with 5 minutes of audio and you need to learn them and generate the samples. So we also evaluated with that data set. The Turkers then rate the samples between 1 to 5 for quality and both similarity. So we evaluate our method on both tasks and we achieve set of that results. Okay, so first of all, the encoder is applied in a sliding window manner. Or basically, it is also able to encode the entire audio. If you have enough memory in your GPU, you can do that. The generation is done in an autoregressive manner. So it's basically one vector from the latent space that I presented, one vector at a time. So it can be done iteratively. So we haven't experimented with that yet. It is possible. There are other works that do what you're talking about, basically helping speech-impaired people to improve their speech. Basically, once you successfully encode the input, you can generate it if you get the data. No, there is no such limitation.
I feel like this technology can help people to attack or imitate other people. So are you taking steps to tackle this problem?
Definitely. So this is probably the same as any other generative models. GANs, for example, are being used for deepfakes. In Facebook, we have a team called AI Red Team, and they are using our technology to develop tools to detect such generated content. So basically, once we have a way to synthesize fake content, we can also generate ways to avoid that. So the main limitation with our method is that we don't change the tempo of the input. Basically, the output will be in the same tempo or pace as the input wave. So if I talk in some specific space, the output will be the different speaker, but the same pace. And in order to change the accent, you need to change a little bit the pace of the phonemes. So basically, some phonemes will be more extended or maybe shorter. And in order to do that, you need some different mechanism. A possible approach is to add some attention mechanism here to solve this issue.